Have you ever stopped to think about what a speeding car, a planet spinning in orbit, and even just the act of you blinking your eyes all have in common? Well, they're all in motion. And today, we're going to pull back the curtain and uncover the surprisingly simple rules that govern how everything, and I mean everything, in the universe gets from point A to point B. Just look around you. Everything is moving all the time. But what's really incredible is that all of it, from a bird flapping its wings to planets whirling through the cosmos, is all run by just a handful of simple rules. Our mission today is to figure out what those rules are, and lucky for us, we've got some pretty awesome cartoons to help guide the way. All right, first things first. Before we can understand the why, we need to get the how. We need to learn to speak the language of motion. So let's break down the 3 absolute key ideas for describing any kind of movement, and we'll get a little help from our friend here, an astronaut named Ringo. Okay, let's start with something we all know, speed. It's how fast you're going, right? Simple, we all get this. And if you remember from school, it's that classic formula, distance equals speed times time. This is our foundation, our starting block. So here's Ringo, just cruising along at a constant speed of 10 meters per second. His movement is totally predictable. After 1 second, he's gone 10 meters. After 2 seconds, 20 meters. You get the idea. It's a nice, steady pace. But what happens if we add just one more little piece of information? And that one crucial little piece is direction. See, that's what velocity is. It's not just your speed, it's your speed in a specific direction. So it's not just how fast, it's how fast and which way. Now, this might seem like a small distinction, but trust me, in physics, this changes everything. And check this out. Look what happens now. Ringo might be moving at the exact same speed, but when he throws the car in reverse, his velocity actually becomes negative. The speedometer needle hasn't moved, it still says 10, but because he flipped his direction, his velocity is now minus 10. Wild, right? Okay, so we've got constant motion down, but let's be real. The world is all about change, and that's where acceleration comes in. Now, most people think this just means speeding up, but it's much more than that. It's any change in velocity. I love how the cartoon puts it here. It's the speed of the speed. Take a look at Ringo's special gadget, the velocimeter. If that needle is perfectly still, his acceleration is 0, even if he's flying down the highway. But the second that needle starts to twitch, either up or down, boom, he's accelerating. And the faster that needle moves, the bigger his acceleration is. So here's a little brain teaser for you. Based on everything we've just talked about, do you think it's possible to be accelerating if your car's speedometer is totally locked in at, say, 60 miles per hour? Not moving at all. Is it possible? Think about it for a sec. And the answer is absolutely yes. Look at Ringo going around this circular track. His speed isn't changing one bit, but his velocity is changing constantly. Why? Because his direction is always changing. Every single time you turn the steering wheel in a car, you are accelerating, even if your foot never touches the gas or the brake. And here's the crucial link, the thing that makes it all click. Acceleration is something you can actually feel. When Ringo stomps on the gas, he feels a force pushing him back into his seat. When he slams on the brakes, a force shoves him forward. That physical sensation, that push or pull, that's a force. And this connection between forces and acceleration is the absolute key to understanding not just how things move, but why. You know, for thousands of years, the smartest people on the planet thought they had motion all figured out. Turns out they were completely wrong, and it took the incredible genius of one man, Galileo Galilei, to come along and just totally overturn centuries of mistaken ideas, setting physics on a brand new path. So before Galileo, the big name was Aristotle, the ancient Greek philosopher, and his whole theory was pretty simple. Everything in the universe has a natural place it wants to be. So things in the heavens, like the moon, they naturally move in perfect circles. And earthly things, like rocks and apples, well, they naturally want to fall straight down. You know, on the surface, kind of makes sense. But this is where the old world of physics just gets completely shattered. Aristotle believed that to keep something moving, you needed to constantly push or pull it. Stop pushing, and the thing stops moving. Seems obvious, right? But Galileo came along and proposed something truly radical. He said an object in motion will stay in motion, going in a straight line at a constant speed forever unless some other force gets in the way. The only reason a sliding puck stops on the ice is because of that invisible force we call friction. This one idea literally changed the world. So let's boil this down because this is the giant leap. Galileo realized forces don't cause motion. No, they change motion. They cause acceleration. This flipped 2,000 years of thinking completely on its head. You don't need a force to keep something going. You only need a force to change how it's going. And Galileo didn't stop there. He also took on the mystery of falling objects. Everybody just knew that heavy things fall faster than light things. A bowling ball will beat a feather to the ground, obviously. But Galileo's experiments proved this was totally wrong. If you can get rid of air resistance, a feather and a brick will hit the ground at the exact same moment. They fall with the exact same constant acceleration. So Galileo laid all this incredible groundwork. But it was another giant of science, a guy named Isaac Newton, who took these amazing ideas and built them into 3 simple, unbelievably powerful laws that could explain everything from that falling apple to the orbit of the moon. Newton famously said, "If I have seen farther, it is by standing on the shoulders of giants," and the giant he was talking about was Galileo. He took Galileo's core insight about how things move and formalized it, making it his very first law of motion. And here it is, the law of inertia. This is basically the universe's default setting. Things just keep doing what they're already doing. Whether that's sitting perfectly still or cruising along in a straight line, they'll keep doing it forever unless something messes with them. And this tendency, this resistance to having its motion changed, is called inertia. Honestly, the best way to think about it is just as the inherent laziness of all matter. And how do you measure how much inertia something has? Easy, it's just its mass. More mass means more inertia, more laziness. I mean, this cartoon just says it all perfectly, right? A big truck has a ton of mass, which means it has big inertia. You need a huge force to get that thing moving from a standstill, and you need an equally huge force to bring it to a stop once it's going. You, on the other hand, have a lot less inertia, which is why you're a whole lot easier to push around. Okay, time to connect all the dots. We've got force, which causes a change in motion, also known as acceleration. And we've got mass, or inertia, which resists that change. So the big question is, how do these 3 things, force, mass, and acceleration, all fit together? It all comes together in one of the most beautiful and powerful equations in all of science. Force equals mass times acceleration. F equals ma. This is Newton's second law. And it's basically the secret recipe for all motion in the universe. It tells you exactly how much oomph you need to accelerate any object based on how much stuff it's made of. This is the absolute cornerstone of classical physics. It's the whole shebang. These laws might look simple on a slide, but they govern literally everything, from a bumpy car ride to the silent, perfect orbit of the moon. You just can't escape them. So next time you're in a car and you feel that little pushback as you speed up, or that lean as you turn a corner, just take a second and ask yourself, what cosmic law am I feeling right now? Thanks for joining me on this explainer.